Hello dear students, welcome you all once again. And I'm Meghamala, working as Assistant Professor from Institute of Aeronautical Engineering, EC Department. And today I'm going to talk about, or else I'm going to discuss something about the definition and terminology from Unit 3, that is Switch Level Modeling. It's Unit 4 Switch Level Modeling. So here in this Switch Level Modeling, as it is a Module 4 from the Verilog as HTL, we will be discussing a few definitions and few terminologies in detail. So coming to the switch level modeling. So as it is a basic definition, or else it's a basic heading of this particular module. So we will be observe what is the switch level modeling. As we have discussed in the previous classes, out of 5 modules, all the 5 modules are comprised of each and every abstract, right? So that means in the Verilog we have so far we have discussed about the behavioral modeling, data flow modeling, gate level modeling and switch level modeling, isn't it? And the last one is logic synthesis. So as these are the 4 modeling which plays a vital role in the Verilog HTL, we will be discussing about the definitions and the different terminologies which come across in this switch level modeling. We will be discussing more about this. So what is the switch level modeling? The switch level modeling is nothing but it forms a basic level of modeling digital circuits. The switches are available in primitives as primitives in Verilog. So as it is one of the major abstract in the Verilog, so all the different circuits, digital circuits are described, or else the digital circuits are constructed, the digital circuits are built with respect to the different switches, okay, based on different switches, and that switches can be observed, or else that switches can be taken from the Verilog primitives. So the Verilog primitives, it consists of, as we have in the gate level modeling, we have the gate primitives, right? The gate primitives can be observed. The gate primitives can be considered from the Verilog library, right? So as well the gate primitives which are observed from the Verilog library. So the switch primitives can also be observed from the Verilog library itself. The switch primitives are observed from the Verilog library, and as well as the gate primitives are observed from the Verilog library as well. Then what is a pull up and pull down in the switch level modeling? So the pull up and pull down are the primitives. Okay, in order to function a proper switch, we need to know whether the switch is acting in terms of pull up or pull down. So what is this pull up and pull down? Are basically they can be used as load for switches or to connect the unused inputs ports to VCC or ground. So here pull up and pull down, in other terms we can say enhancement mode and depletion mode, right? So enhancement mode and depletion mode are they are similar to this pull up and pull down switches. So these switches are nothing but they are used as a loads. Okay, they are used as loads for the switches and also to connect the unused input ports. So in order to connect the unused input ports, so we know in proper circuit diagram, we'll come across the power sources, right? We come across the VCC as power sources and ground, okay, VCC or ground, and also we have the inputs and as well as we have the outputs and the connecting devices, also connectors we see. So in the circuit diagram, if you observe, we have the VCC power supply and the earthing ground. So in order to connect the unused inputs, that means what? To connect the VCC, okay, and also to connect the ground, basically this pull up and pull down primitives are used. Okay, so you will observe this pull up and pull down primitives in the switch level modeling. And coming to the directive. So how can we define directives? So not only in the switch level modeling, in some other in the other different abstractions, we have different types of what do we say, directives, right? So these directives will help us to drive the signal. So here the directive is used to define and associate the desired text with the macro name. Okay, so here this directive, we are defining this directive as it associate the desired text. It associate to some text. Okay, so each and every individual text are being associated with some directives. So particularly this text 1 is associated with some directive and this text 2 is associated with some directive. So likewise, and for each directive we are giving a macro name, a big name, or else a name which is of many characters which are included. We are giving such macro name defined as like this. Define, add 2-bit of binary. Okay, 2-bit of binary, bits 2 be 0, 0. So this is how we will represent or else give the name of particular directive. Okay, and this kind of directives we have in the switch level modeling as well. Coming to the bidirectional switch primitives. So as we know that in the Verilog library, in order to obtain some switches from the library, we can easily access, right? So in the library, one of the primitives, okay, one of the switch primitives that we can observe or that we can grab from the library or Verilog library is nothing but bidirectional switch primitives. So what are these bidirectional switch primitives says? They include the Verilog library that includes 6 predefined bidirectional switch primitives. So these bidirectional switch primitives are of 6 kinds, 6 types. They are tran, rtran, tranif0, rtranif0, tranif1 and rtranif1. So here these are all the 6 types of switch primitives, bidirectional switch primitives we can say. That means what? The currents and the voltages, they can come and go simultaneously. The simultaneously occurrence of current and voltages can be observed in this bidirectional switches. So the bidirectional switches are of 6 types categorized. They are tran, rtran, tranif0, rtranif0, tranif1 and rtranif1. So what is rtran and rtran? They differ with the resistive. We call this as a resistive transistor. So here resistive transistor if 0, resistive transistor if 1. So that is how the switch primitives can be easily observed. Then, so the rtran and tran are the primitives. They are modeled bidirectional pass gates. So as these are called as bidirectional switches, they are modeled the bidirectional pass gates. Okay, the gates which are designed by using this bidirectional switches. So we are calling it as bidirectional pass gates and may not have a delay specification. So here, if the gate is observed or if the gate is constructed with the help of this bidirectional switch that is tran or rtran, then we can call that as such kind of transistors or such kind of devices or the circuits. They may not have the delay specification. Okay, there's no need to represent the delays. The delay specifications cannot be observed in this tran and rtran primitives. And then rtranif0 and rtranif1, tranif1 and rtranif1. Switches are accompanied by delay specifications. So, as we know that we have totally 6 switch primitives, right? So, out of these switch primitives, we are saying that tran and rtran. So, tran and rtran switch primitives, they may not have the delay specification. So, there is no need to observe these delays. But whereas the other 4 categories, the other 4 types of switch primitives, we can easily or else we can they are accompanied by the delay specification. So this is one of the important point to be discussed or remembered. Then what are primitive gate and switch type? Primitive gate and switch type. So here in the Verilog library, we have primitive gates and also we have the switch type. So what are the primitive gates and what are the switch types? So here the mentioned things are the primitive gates and the mentioned things are nothing but the gate type, switch type things. So here in the CMOS switch type, we have the CMOS, RCMOS, and MOS switch types we have NMOS, PMOS and RCMOS and RPMOS. The combination of the normal PMOS, the switches with respect to the N and P type and also with respect to the resistors, and then pass switches. So one is CMOS switches, MOS switches and pass switches. So the pass switch types we have the tran and rtran. Coming to the gate, okay. So coming to the gate primitives, we have enabled gate type. So in order to the enabled gate type, the primitives goes buff if 0, buff if 1, not if 0 and not if 1. And then coming to the N input gate type. So we have n input gate types and n output gate types. So here in this n input gate types, we have all the basic gates. So why we are saying it as n input gate type? Because we can give n number of inputs to such gates and n output gates. So for this n output gates, only one gate we can specify clearly, that is nothing but the buff or not. Okay, so buff and not, already we have discussed the difference between these two gates. So as these two are the two different gates, where not resembles that if the input is 0, the output is observed as 1. Whereas if it comes to the buffer, when the input is 0, output is observed as 0 itself. When the input is 1, output is observed as 1. So that is the difference between the buff and not, as they both indicate the same, but the mechanism or the functioning of the two different gates of not and buff are bit different. So here we say the n input gate is buff and not. Coming to pass and switch type. So we have CMOS, NMOS, CMOS, MOS, pass and pass enable switch type. So in this pass enable switch type, we see the primitives goes with tranif 0, tranif 1, rtranif 1 and rtranif 0. So all these are the primitives which they comes under the pass and transistor or its pass enable switch type. Okay, so these are the two different primitives, switch primitives and gate primitives, that we can observe from the Verilog library. And coming to the tranif 0. So what does this tranif 0 means? Tranif 0 is one of the bidirectional switch. Okay, out of these 6 bidirectional switches, tranif 0 is one of the bidirectional switch where it connects two signals, in out 1 and in out 2. Okay, where it connects two signals, in out 1 and in out 2, only if the control signal is logic 0. So only if the control signal, as I said you, in this when you are considering the switch analysis or it's a switch modeling, in the switch modeling, for each and every module that you are constructing, we have to make sure that along with the inputs and outputs, there is another input to be considered, that is nothing but the control input. Likewise, in the multiplexers and demultiplexers, we have inputs and output as well. But the output is derived with respect to the selection lines, right? So in the multiplexer, as we have the selection lines, the output is derived. That is 2 by 1 mux. So in the 2 by 1 mux, we have input as I0 and I0 and the output as 1. Why? But based on the selection lines, okay, selection lines, based on the selection lines, the output is enabled. Either it is enabled 0, I0 or I1. So likewise, in the switch primitives, we have, that means in the multiplexer, when you're writing the code, we will write like this: module, multiplexer, okay, name of the multiplexer, and in the port list, we will mention the output as well as the input and the selection lines. So likewise, in the switch level modeling, in the port list, we will be writing the inputs, output and in-out ports in terms of Y, I0, I1 and the control input. So based on the control input, the output is observed, right? So the tranif 0 is a switch which connects two signals, in out 1 and in out 2. If only how this bidirectional switch is connecting these two, how is, this is rtran if 0. This is a switch where it is connecting in out 1 and in out 2. It will connect both in out 1 and in out 2 if and only if the control signal is logic 0. When the control signal is logic 0, then in that case, the bidirectional switch rtranif 0 can connect both the signals, input 0 and input 1 and input 2. If it is, for example, the control signal is 1, then it may not connect these two. So that is what the tranif 0 is. Then if the control signal is logic 1, then the non-driver signal gets high impedance Z. So if it is logic 1, when the control signal is logic 1, then it goes, the output or as the connection, the signal, the control signal, if it is logic 1, then the non-driver signal, the signal it may goes the high impedance level, that is Z. Okay, if only the control signal is 0, then the tranif 1 can connect both the signals, that is input in-out 1 and in-out 2. If it is 0, then it may goes, or else the output value, it may goes beyond, that is the high impedance value Z. That is about the tranif 0. Then the driver signal retains a value from its driver. Obviously, the driver signal, if it is taking its initiation with respect to 0, 1 or Z or high impedance, what happens is, once it gives the signal, then obviously it retains it. It takes it back. Okay. It takes it back the value from the driver itself. Then the module, say here a small example he has given. Module, okay, description given for some particular circuit, the name of the circuit. Then input, control signal and output. So inputs are IO1, control signal resembled as control, and the output as IO2. Then I'm using the tranif 0, right? So the tranif 0 is connecting the two signals. So tranif 0, based on the control signal, the output is, the input signals are connected, right? So input IO1 and IO2 and the control signal. And finally, ending the module, end module. Started with module, end with the end module. So that's how the R tranif 0 is defined in the switch level modeling. Remember that R tranif 0 is one of the among six switch primitives. R tranif 0 is one of the bidirectional switch where it connects the two signals, in-out 1 and in-out 2. Only it connects if only the control signal is 0. If the control signal is 1, what happens is the driver, it drives out the output to the high impedance value, that is Z. Okay, and this is how the representation takes place. Strengths. Coming to the strengths in the switch level modeling, based on the strengths, okay, based on the delays, based on the strengths, we will be observing the output, or else the proper delay configurations can be made out. So now we will describe what is a strength. Strength is nothing but it is a value carried by the interconnections and abstracted from the whole range of analog voltage or currents, analog voltages or currents to a small number of discrete values. So to a small number of discrete value. That means the strengths are nothing but they are some values. Okay, strength is nothing but they are some values where the signal carried out some values. Okay, the signal will have some values carried by the interconnections. Okay, the two signals, they carried by the interconnections and are abstracted from the whole range of analog and voltage currents to a small number of discrete signals. That means what? When the two signals are connected, okay, when these two signals are interconnected, that means what? It gives the output in terms of discrete values. So the outcomes would be with respect to the voltage, analog voltages or current. The range of inputs, the range of the voltages and currents can be observed in terms of discrete values. That's nothing but the strengths. The strengths of the signal can be carried out with respect to the voltages and the currents. And the voltages, the values of voltages and the current, the analog voltages and the analog currents, the values of analog voltages and the analog currents can be observed in terms of the discrete values. So each and every signal will be carried out with some strengths. Based on the strength, we can easily make out whether the signal is strong or whether the signal is low. Okay. Then coming to tran and R-tran. So previously we have discussed about tranif 0, right? So tranif 0 is one of the bidirectional switch from the switch primitive. And now we discuss what is tran and R-tran. So tran is a gate. Tran gate is a bidirectional gate of 2 ports. Okay. So this R-tran is a bidirectional gate of 2 ports. When instantiated, it connects the 2 ports directly. So tran, it connects the 2 ports, 1 and 2 ports directly. The syntax goes like this: tran, S1 and S2. That means S1 and S2 are the 2 ports where it connects directly. Okay. Then here connects the signals lines S1 and S2. So tran is a switch, bidirectional switch, where it connects the 2 signals, or else it connects the 2 ports S1 and S2 directly. Okay. So and R-tran is opposite. That means what? It is a resistive switch. Okay, the resistive switch also functions same like the TRAN as well. Then coming about the capacitive store. So what is this capacitive store in the switch level modeling? So capacitive store, all drivers on the net have high impedance values. So obviously the drivers, it drives the values, it drives some values based on the strength of the signal, right? So all the drivers on the net, they have high impedance value. So we represent the high impedance value as Z, and we represent the don't care condition value as X. So it could be of 0 or 1. But the high impedance value is nothing but the saturated value, where the net holds the last driven value and the strength is small, medium or large. Default is medium. So by default, the strength of a particular signal is considered to be in the medium level. Okay, but we may see some signals, they may be in terms of small, or else they may be in the very low. Okay, very large or small. But in fact, by default, we will be considering the signal which is carrying out some values, okay, some strengths or the driven values. It could be in terms of, by default, we'll consider it in the medium scale, right? So the capacitive store, the storage, the net which is driven by the different values, it could be in terms of the medium, okay, medium. Then coming to the classification of timing control. So timing control are classified into 3 types. Okay, one is method of timing control, second one types of delay based timing control, and types of event based. So timing control, delay based and event based. So when you are by hearting this definitions, you have to mean it a lot. So by based on the name of a heading or its name of a particular module, you can able to get out the answer. So here coming to the methods of timing control. So what are the methods? So we have delay control and event based timing control. So the name indicates here the delay based timing control. So in the timing control, they are categorized into 2, event based and as well the delay based. So delay based timing control is nothing but regular delay control and intra-assignment delay control and zero delay control. So again, it is subcategorized. The delay control, delay based timing control is again subcategorized into regular delay control, then intra-assignment delay control, and as well as zero delay control. Then coming to the event based. Okay, so in the event based timing control, again it classified as regular, named event, event or and level sensitive timing control. So here when it comes to the delay based, in the delay based, it has subcategorized again into three types: regular, intra and zero. Whereas in the event based, it categorized into 4 based on the level sensitive timing as well. Okay, level sensitive timing, event or control, named event and regular event. So all such kind of delay based timing control we will be observing in the switch level modeling when you are supposed to carry out the signal from the input to the output. Okay, when the connections are made internally or externally, whatever with not with respect to the connections, but the mechanism goes as per the timing delay control. Okay, then coming to the needs for switch level models. So what are the needs for switch level models? Now needs, we need to concentrate on the needs. Why we are going for the switch level modeling and why do we need this? Why do we need this? So switch level modules are used to allow detailed constructions of logic gates. So the name indicates it's a switch level. So in order to switch different gates, okay, to connect, or else the construction of the logical gates and functions, and also to allow complex delay modeling to be used. So this is a switch level modeling where the connections would be made in terms of the gates. All the different gates would be connected together and the switching mechanism of all the different gates would be modeled as per the abstraction considered. So here the gates and the functions are they also to allow complex delay modeling which is to be used. So when you are designing some module based on the gates, okay, the switching of the gates can be carried out in order to observe a complex designing and also a normal designing as well, which is to be considered, which is to be used. Then What is meant by continuous assignment in Verilog HDL? In the Verilog HDL, the continuous assignment is, it's a most basic assignment in data flow modeling. In the data flow modeling, we have come across different types of assignment statements. So one of the assignment statement is continuous assignment. So here in the continuous assignment, the execution of the statements would be concurrently executed. Okay. So sequentially, concurrently, the executions will take place. Then the continuous assignments are used to model in the combinational logic. And then finally, it drives values into the nets, and the syntax goes like this. So net, strength of a signal, and the range of a signal if it is low, medium or high. And here the specification of delay, 10 nanoseconds, 2 nanoseconds or whatever, and the identifiers. So identifiers are nothing but one of the tokens from the Verilog, where we represent in the syntax form if you are using any kind of, if you are switching, or else if you are if you want to get a proper output in terms of delay constraints, then the identifiers plays a vital role. Then this is a assignment operator, and on to the right of the assignment operator, now we will see net or register. Okay, the expression will contain some values. The expression will contain some the coefficients where they store the information. So it could be in terms of nets or registers. This is the syntax, and then we are writing in the data flow, right? So in the data flow, assign is a keyword. Okay, assign, strength, delay, then net, which is equals to net or register. So this syntax is nothing but this. This is written in terms of what do we say? In terms of data flow modeling, where the concurrent, the execution of these statements goes with respect to concurrently the execution of the statements goes. Then the difference between while and reg. So what is this while and reg? They are the nets. Okay, they are nothing but the variables. They are the nets for the interconnection purpose. So we'll see the net type, wire and try, physical connections between the structural elements. So as we have discussed in the previous class, the wire and try, they are nothing but the connectors. Okay, they connect. So for the complex designing, we go with respect to the try, and for the simple things, we go as per the wire. So they are the connection, physical connections between the structural elements. And value assigned by continuous assignments or a gate output. So here the value which is assigned by the continuous assignments or the gate output. And then coming to the register type. So the register type are reg, integer, time, real time. So in the register type, sort of connectors, that is all these things comes under the register type, where here they represent the abstract data storage elements. So here, as they store the memory, as they store some data or the information, so this represent the register type represent the abstract data storage element. They store some sort of information or the data. Then the assign values only within an always statement or an initial statement. So the whatever the assigned values, so whatever the registers that they are holding some values. That means here, for example, register I is equals to 10. So in my code, I have written register I is equals to 10. That means what? It's holding some value, right? It's holding some information. So we will assign, this information is being assigned to I. Okay, question I. So assigned value are only within the always statement. So it must be right within the always at the rate passage clock. If you are considering any flip-flop, passage and register, then initial, okay, begin, and statement goes for, if you are using any for loop, for I is equals to 0, then end, initial, begin, end, then end module. So this is how the code should be written. But always remember that the register type sort of nets can be written only in between the always at the block and as well as the assign. Okay, then coming to the main difference between wire and reg. So now we will see the main difference between the wire and the reg. So wire cannot hold or store the value. So we know that wire is a connector where it's used only for the connecting the different elements, where it cannot store any sort of information. It just acts as a physical element where it connects the different gates, right? So it cannot hold any sort of information. Wire cannot hold or store the value when there is no connection between A and B. So if you have any A and B and some information it should pass from A and B, then what happens is we cannot store the information which is having A cannot be passed to B through wire. Wire is meant only just to connect A and B. Okay. Then if there is no connection in A and B, wire lose value. So if there is no connection between A and B, what happens? Obviously there is no connection and there is no purpose of using the wire. Okay. Then coming to reg. Reg is nothing but it holds a value. Okay. It holds a value. Wire doesn't hold a value because it acts as a connector between the two elements. But whereas reg is, it holds a value even if there is no connection. Right. So even if there is no connection, it holds a value. It holds some information into it. Then by default, wire is Z and reg is X. We can say that wire is Z. So we can say wire acts as a high impedance value. So it doesn't matter a lot. But whereas X is reg is Z, reg is X. That is, it can store either 1 or 0. Any sort of information can be stored in the reg, but not in the wire. Then what is a capacitive store? So capacitive store is all drivers on the net have high impedance Z values. We know that in the net, all the drivers, okay, they have high impedance value basically. And the net holds a last driven value. So this net, in the, just now we have discussed reg and wire. Where wire, it does not hold the information, whereas reg holds the information. So this reg, it holds. The capacitive store is nothing but the driver, whichever he is holding a particular element or is a net called wire or reg. That means what? It holds the last value and the strength of this reg. Okay, the strength of this reg, it could be either small, medium or large. Basically, by default, what happens is we say that the proper signal, it could be in terms of medium level. Okay, and then coming to tree reg. So tree reg is also one of the net where it is is used to model net having capacitance or store value. So here reg, wire are nets, whereas tree reg is also a sort of net. Okay, a sort of net in order to store the value. So okay, in order to store the value, we are making use of some net, some variable where it holds some information, right? So just for the capacitance storage, okay, the capacitance storage, we are making use of this tree reg. And by the default strength for tree reg nets is medium, and the default value is the X. So the default strength, okay, the strength of a particular signal based on the tree reg is nothing but in terms of medium level, and also the default value is X. Then what define pin-to-pin delays? So what is this pin-to-pin delay? Pin-to-pin delay is pin-to-pin path of a signal may change depending on the value of other signal. So the pin-to-pin value, the value of pin-to-pin, for example, if it is 0, obviously to the second point it should get 0, right? But what we are saying is the value or as a signal may change. The pin-to-pin path, as per this path, the signal may change. If it is observed 1, it may observe as 0, or if it is 1 or it is 0. So the signal may change depending upon the value of other signal. So depending upon this value signal, the input whatever given to this particular pin can be changed. Okay. So in turn, the number of circuit elements in the alternate path may differ. So in the alternate paths, for example, here I am sending my signal as 1. But as per this, my signal should be 1 I should send. So which is different, right? So if it is 1, I should send the signal 1 to this path. Then only I can reach. If not, what happens is I can choose the another alternative path. In the another alternative path, I have to make sure whether the destination is 0. Is it matching with the with me or not? I should check. So this is nothing but the pin-to-pin delay. When you are checking in the alternative path, you will be observed obviously some delays, right? So such delays are meant to be as pin-to-pin delays. Now we will see to specify if f is equals to 2 bit of 0, then what happens? A is D, which is equals to 1. If f is greater than 2, what happens? A is D, 2. So here if you observe, we know this is equal to and we know this is 1, right? And now we will see CI input is multiplied with output. Input is multiplied with output, which is equals to 1, and end specified. So here we are multiplying, okay, we are multiplying in order to match the destined point. Okay, in order to match the destined point, we are just going with the multiplication as well as with the greater than symbol. So here, if you observe, we see the concatenation of both the signals is observed. Okay, so in maximum times, we will not, the pin-to-pin delays will be observed very low, very less. Okay, so this is the pin-to-pin delays. And now, specified blocks. So what are the specified blocks? Module paths are defined and values assigned to their delays through the specified blocks. So through this specified block, what happens is the paths, the module paths, okay, and the values, the paths and the values are assigned. So these nothing but through this specified block, the values and the paths, are assigned. They are used to specify. So this values and path, they specify rise, fall and path delays, pulse width. Okay, so this values and the paths, they specify rise time, fall time, okay, turn off time, and the width, pulse width. So now we will see here specify is a keyword where we need to specify the delays, okay, or the time delays or the width of the signal. So we are using a keyword called specify. Spec param, rise time, okay, which is 5, and the fall time is 6. So now A is greater than B, that is rise time and fall time. So we can say that this is a 2 format delay specification. 2 format delay specification. This is already we have discussed in the previous class. 1 format delay, 2 format delay and 3 format delay. In the 1 format delay, we specify only 1 time. Whereas in the 3 format delay, we specify rise time, fall time and the turn off time. So C greater than 0 is 6 and 7. So here if you observe, we have A and B, we have C and D. So A and B is rise and fall time, where we are presenting it with 6 and 7, and then finally end specified. So the value which are meant for rise and fall are 6 and 7, and we are specifying in this path delays, pin to pin or else specified blocks, using specified blocks. Then what are module parameters? So parameters are nothing but they are associated with the size of a bus. Okay, they are associated with the size of a bus, registers, memory, ALU and so on. So the parameters include, if you are modeling some device, the parameters goes with respect to the buses, different interconnectors, memory devices, memory elements, registers, logical units and so on. So these are nothing but the module parameters. They can be specified within the concerned module. So if you are modeling 3 different modules, module 1, module 2 and module 3. So for module 1, I need some parameters, and my parameters, it would be in terms of registers, registers, memory, ALU and buses. And this, the parameters which are meant for this is different from the M2. And the parameters which are meant from M2 may differ from the M3. Okay. So, but their values can be altered during instantiation. So obviously, if you are considering 3 different modules, the instantiation of the parameters will differ. If you are giving a memory as M1 for module 1, obvious M1, M2, and for module 3 we will get M3 and M4. Or else for module 3, M4 and M5. This is how the different initializing the parameters may differ. Then, what is zero delay? Zero delay is a delay is 0 nanoseconds, called the zero delay. Obviously, if it is 0 nanoseconds, 0 is 0 delay. Okay, 0 nano. If it is 1 delay, 2 delay, like that. And it does not really cause any delay. So obviously, as the name indicates, is zero delay. It means what? No delay is observed. Okay, no delay is observed. And then C, delay 0, C is equals to A and B. So in A and B, there is no delay is observed. So this is about the zero delay. And the difference between module and instance. So what is this module? Module is nothing but a basic building block where it has the input, outputs and in outputs. Okay, inputs, outputs and in outputs. And then the module have unique identity and they differ from other instances of the same module. So they have the unique identity. So if you we have exit and we have enter, we enter the inputs and we exit the input. For each entry and exit and in-out ports, the instantiation differs from module 1 and module 2. And each instance has an independent copy of internals of module. So each instances, whatever we are initializing, they have or else they depend on the copy of the internal module. Okay. So for example, this is my module M. So internally my input goes like module M1, module M11, I1, module MI2 like that. Then what is mean by triggering flip-flop? So flip-flop, triggering of flip-flop. Triggering is nothing but switched. Flip-flop is switched by a momentary change in the input signal. So we know that flip-flops, we have different types of flip-flop. D, S, R, T, right? So the flip-flop is nothing but it is a momentarily switching between the input signals. The momentary change is called the trigger. Momentarily change is called trigger. Abrupt changes, if you observe in the input, then it's called nothing. It's nothing but the triggering. So triggering, the abrupt changes is nothing but the triggering, and the transition it is caused is said to trigger the flip-flop. The transition is which is occurred. The abrupt transitions or the abrupt changes which is occurred is nothing but the trigger, and they can be causes. Okay, they can be causes to trigger the flip-flop. That is nothing but the triggering of a flip-flop. So this is about the definitions that we come across and the terminologies we come across in the switch level modeling, which is a module 4, switch level modeling, one of the basic abstraction from the Verilog VHDL. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.